Okay, welcome back to chapter 19. We're in section 19.8 of this really long chapter. This chapter is entitled Nucleophilic Addition of Amines. Okay, and more specifically, we're looking at imine and enamine formation. So these are different functional groups that you're going to learn about in this chapter, imines and enamines. But we kind of have to go back to the beginning to remind ourselves just what are amines. Okay, remember they're all Lewis bases, and so the reason they're basic is because they possess sp3 nitrogen with a lone pair. All right, and so if you have an NH2 at the end, that's a primary amine. If you have two R groups attached to the nitrogen with one hydrogen, that's secondary, and those are the ones that we're looking at, not tertiary amines. And as you know, we just said amines are Lewis bases, so they act as nucleophiles, and so the reactions we're going to look at here primarily are attacks on carbonyl, primarily that of aldehydes as well as ketones. So let's go ahead and take a look at what's going on here. I first have a sort of a generic perspective that we have a primary amine, okay, we have an aldehyde, or you could have a ketone here, and when you do that you generate an imine. Okay, so let's go to the next page and take a look at how that process works and remind ourselves what an imine is. So I'm looking at the very top of page 132 for an example of how you form an imine. Now, if you'll look on the left-hand side, we have our good friend benzaldehyde, all right? And here is a primary amine called propylamine. So this is a primary amine. Now, it's very important that you distinguish the kind of amine that we have here. This is primary because it has one carbon attached directly to the nitrogen, and all of those always have two hydrogens. This is an aldehyde, benzaldehyde, you've seen it before, but this could also be a ketone. Now, as you can probably tell, we're going to connect the nitrogen here to the carbonyl carbon with a double bond. So let's go ahead and highlight our double bond. Right? So a carbon-nitrogen double bond like that is called what? It's called an imine. So this is a specific example called benzalidene propylamine. An example of an imine. Now, years ago, we used a form of chemistry called lasso chemistry, whereby we would put a lasso around certain nuclei and join the other atoms with a double bond. Now, what I'm talking about here, look at the byproduct, water. Okay? So what elements constitute water? Two hydrogens, one oxygen. So if I do a circle, okay, or a lasso around those elements there, what do you see inside that circle? You see the elements that constitute water, okay, right? And so in effect, that's where the water's coming from. So really all that you had to do was join, okay, join this carbon to that nitrogen with the double bond. So let me just write that down. Join with double bond, right? And when you do that kind of thing, you end up with an imine, as you see on the right. So it's really easy to figure out how to generate an imine. Now, there are a number of contingencies associated with imine formation, right? If you go to McMurray, he shows you a general mechanism for how imines are formed. There's also enamines, and we'll look at that here in a moment. But all of these are involved in equilibrium. Generally, you can shift the equilibrium in the laboratory by any number of means. One way is to precipitate that out, or via distillation, so on and so forth. But the most dominant way to shift the equilibrium is by removing the water. Okay, so if you look up here, right, there's water, and so if you have the means of absorbing that water or distilling that water, azeotroping that water, the imine formation is going to proceed to the right. Okay, now let's shift to enamines. To get an enamine, it's a little bit different. We're going to have secondary amines. You can have an aldehyde or a ketone again. Those are going to give us enamines. Okay, so keep that in mind. Secondary amines plus aldehydes or ketones give us enamines. So here's your general example. A little more challenging though to see how that works. Notice here that we have an aldehyde, and here we have N-diethylamine. This is the secondary amine. Okay, so we can't use lasso chemistry like we did up there because the water we're generating is not a result of two hydrogens on this nitrogen. Okay, something else must be going on. Well, let's move over to look at why this is called an enamine. The ene part of the name, okay, the ene part of the name comes from alkene. So we have a carbon-carbon double bond. That's where that comes from. We call it an ene, like an alkene. And of course we have an sp3 nitrogen, and that's where the amine part of the name comes in. So henceforth this is called an enamine. So make sure you see the difference between an imine, which is a carbon-nitrogen double bond, versus that of an enamine, which is a carbon-carbon double bond flanked by an sp3 nitrogen. Okay, so these work out differently. But again, you can shift the equilibrium towards the enamine by removing water in the laboratory to provide you with the desired enamine. Okay, now what's your job? Your job is to figure out the structure of an enamine, right? Well, how did you know that we needed an enamine in here? Well, I just said so, but the real reason you would know that is because here we have a secondary amine. If you have a secondary amine, you're going to form an enamine. Now, this happens to be a ketone, but it also could have been an aldehyde. Okay? Let me show you the simplest way to go about this, and then we're going to go through the mechanism a little later. You know that you're going to join, okay, the nitrogen, okay, to that carbon via nucleophilic attack. All right, that's going to happen. So why don't we go ahead and set this up with the basic backbone. All right. In other words, there's my cyclohexyl ring system. Okay. Here's the nitrogen. That nitrogen bears two methyl groups. All right. And so you're almost done, but if you'll use this as the model here, notice there's a double bond adjacent the sp3 nitrogen. So we can place a double bond here, okay, or there, and we're done. So if you're asked to predict a product, you say, well, a secondary amine, aldehyde, or ketone, we're going to get enamine. So this would be our enamine product. Okay. This will be our enamine product. Now, enamines, it turns out, themselves, they're nucleophiles. Okay, but we're not going to discuss how you can use them as nucleophiles. If we went deep into chapter 22, which we won't, we would discuss that. But just remember how an enamine is formed. Okay, let's go ahead and move to page 133, because I promised you that I was going to talk about how enamines are actually formed. So this is the same reaction we just saw on the bottom of page 132. Okay, the distinction here is that, okay, I've drawn it out in a little more detail, but we're also going to look at how it happens. Now, the one thing I didn't mention because I was saving it for now, okay, is that this reaction proceeds more rapidly if we have a catalytic amount of acid. Okay, do you see a catalytic amount of acid anywhere? Okay, yeah, there it is. Okay, written right below the reaction arrow. Now, it's not essential to have that, but it speeds up the process. So this is our catalyst. Now, one reason I mentioned that is because you know that the catalyst has to reemerge at the end of the reaction, right? But again, it makes the reaction go a lot faster. So what's going to happen in step one, we're just simply to provide the curved arrows, right, is that we're going to protonate, the carbonyl oxygen. So that bond here will break. So we've needed 2 curved arrows so far. This intermediate is a much more powerful electrophile than this. Anytime you protonate the oxygen, you're going to end up with a very, very potent electrophile. Now, you can tell in the next step that here the secondary amine is going to act as a nucleophile. It'll come right there, okay, to form a bond between the carbon of the protonated carbonyl, and as you've seen many times before, that pi bond will become a lone pair directly onto the now sp3 oxygen. So here's another intermediate, okay, as a result of that nucleophilic attack. Going from here to here is pretty simple. It involves the transfer of this proton. This proton now is quite acidic because it's part of an ammonium salt. And this can happen intermolecularly or intramolecularly. Let's just show it happening, okay, intramolecularly. In other words, to do that, I'd use one of these lone pairs. We grab that proton, and it's not unreasonable for that to happen because this proton is pretty close to that lone pair, and then this pair of electrons, okay, would become a lone pair of the nitrogen. So that leads us to an intermediate, simply from that proton being scrambled about. Now at this point, okay, we could have one of several things happen. But let's just go ahead and show this as if it were an E2 mechanism. I think that might be easiest to do. Water is a good leaving group. Okay, so if water were to leave, all right, then we could form a double bond here. So one way to show that is recognize that probably what happens, the water breaks off, but it's not unusual to anticipate that water here is going to function as a Lewis base, or Bronsted-Lowry base, I should say. And then we have the elimination occur like that. So the set of curved arrows I'm drawing here is E2, but this probably can happen by way of an E1 mechanism just the same, E1 or E2, but what I've shown is E2. And what happened in the process? Did we get our catalyst back? Yes, we did. When we form a bond between the oxygen here and this proton, we regenerated our catalyst. So this is the mechanism for enamine formation. So I have a few notes here about that, okay, and why we're doing what we're doing here in this particular section, okay. For characterization purposes, derivatives of aldehydes and ketones are prepared, okay. Now you may not remember, but you've actually done this kind of thing in the lab back in Organic 1. So what we're going to do is learn how we can make a derivative, okay, that is something that we can actually crystallize and take the melting point and then figure out what it is indirectly. So there's 2 examples. One of those is the formation of oximes, and the other one's called the formation of 2,4-DNP derivatives. Let me show you how this works, because they both kind of work the same. Notice we have cyclohexanone here. This could be an aldehyde or ketone. So let me show you how you form an oxime. Some people pronounce that oxime, I pronounce it oxime. You're going to form a double bond between nitrogen and this carbon. Have we seen that before? So this is another good candidate, okay, because this is hydroxylamine. I'm going to go ahead and use lasso chemistry right there, and you can see the elements that constitute water inside that. There's your water byproduct. And yes, you can speed this reaction up with a catalytic amount of water. I'm sorry, catalytic amount of acid. So what do we do, though, to figure out our product? You join those with what? You join with a double bond. Let me abbreviate double bond DB, save some time. This makes cyclohexanone oxime. This is a very important compound. It's used to make what we call caprolactam. Okay? And then caprolactam is used to make nylon. So this is a very prominent industrial reaction. So this is how you make an oxide. Well, how do you make 2,4-D and P derivatives? These are okay. These work pretty much the same way. The compound you're looking at here is called 2,4-dinitrophenylhydrazine, and it has 2 nitro groups, which means either very electron withdrawing, but that's going to result in having a stable compound later. And we have 2 nitrogens, both are sp3, but this one's way more basic, okay, because it's not bonded to the aromatic ring, and so there's no electron donation. So this is a very basic nitrogen. So let's go ahead and use our lasso chemistry again. So I don't remember doing this in Organic 1 lab, but what do you see inside that lasso? You see the elements that constitute water, okay? And how did you figure out your structure? You did the same thing as you did above. You joined this carbon to that nitrogen, right? With the double bond. I'm just going to write join. Join them together and with the double bond. And you can see the double bond in both cases. So now this is acetone 2,4-dinitrophenylhydrazone. When you crystallize it, you can take the melting point, okay, and then look up in a table, and it would tell you, okay, what the identity was, and then you could figure out indirectly that the ketone that you began with was acetone. So this is used for qualitative analysis in organic chemistry, and to figure out structures of unknowns, mostly for sophomore organic labs. All right, now let's move to the next section. Next section appears to be very similar, but it's going to give us some very different results. This is called nucleophilic addition of hydrazine, and specifically known as the Wolff-Kishner reaction. Some people call that the Wolff-Kishner reduction. Now hydrazine looks like a pretty innocent compound, but it's not. Okay, hydrazine is a very toxic, okay, extremely toxic compound, a very, very powerful reducing agent. Okay, there's hydrazine. So, but how does this particular reaction work? Well, here's what's going to happen. The Wolff-Kishner reaction or reduction allows for the conversion of aldehyde ketone carbonyls to methylenes. Okay? So folks, the carbonyl, the C double bond O, is going to be converted to a CH2. In order to do this, you simply need hydrazine, stoichiometric amount, and a stoichiometric amount of a strong base, such as potassium hydroxide. So here's our generic example. And we have an aldehyde or ketone, hydrazine, aqueous base. Look what happened. Where you formerly have this carbonyl, okay, it's been converted to a methylene. So this is a way to do that. And of course you have nitrogen gas, which evolves, and then water is also another byproduct. So we're not going to go through the mechanism on this one, but it's kind of related to the ones that you saw earlier. So what's your job? Simply to figure out what products you get. It should be relatively simple. So we see hydrazine on top of the arrow, we see aqueous base on the bottom. So what's going to happen? Well, the hydrazine is going to attack the carbonyl in both cases, but those carbonyls ultimately are going to become methylenes. So yes, we go from cyclohexanone to cyclohexane. Now, while it's not necessary to do this, let me just go ahead and sketch in 2 hydrogens there to help make the point that that's what's going on. Okay? And of course, you're not responsible for the byproducts, but yes, you would get nitrogen gas bubble out, and you'd also get water, okay, as a byproduct here. But the reason you did this was to convert it into that organic compound. Similarly, you can take acetophenone. Acetophenone, one of those compounds we want to commit to memory. And so where you formerly had a carbonyl, what do you have there now? You've got a methylene. So this is a way that you can convert acetophenone into ethylbenzene. Okay? And of course nitrogen and water prove to be our byproducts here. The nitrogen evolves, the water stays behind in the liquid. So that's the Wolff-Kishner reduction. Now we want to move into another realm that involves nucleophilic attack at carbonyls. This one's something maybe you haven't seen before, but later, particularly for those of you who study biochemistry, you're going to learn about these kinds of things. This is entitled Nucleophilic Addition of Alcohols, and we're going to form something called acetals. All right. So as I had noted, folks, part of biochemistry is carbohydrate chemistry, and so it's very important to carbohydrate chemists. And it's usually going to involve a reaction with an aldehyde or ketone and alcohols. The process is reversible. We'll see that. And in all of these cases, they're going to be catalyzed by a trace amount of some acid. So here's a general example of what's going on. Your organic substrate includes aldehyde or ketone, and you can have a primary or secondary alcohol, or it can even be a methanol. Because methanol is pretty common for this. Notice we have 1 mole, all right, of the ketone. We have 2 moles of the alcohol. And yes, we probably have a catalytic quantity of acid here in order to favor the forward formation of the acetal. So what are acetals? Acetals have oxygens, 2 of them bonded directly to the sp3 carbon in the center. And so this is kind of a general name. But if you start with a ketone, sometimes they call those ketals, all right? But it's still an acetal. Okay, let's flip over to page 135. What I have on page 135 is an example of acetal formation, or specifically ketal. So all we're asked to do here is provide the curved arrows for this process. Now I'm going to start here, okay, and work our way all the way around down to here, okay, until we get to this final product. So this mechanism you're looking at is for the reaction that you see inside this rectangular box. And we're going to use a catalytic amount of acid to help us get a firmer grasp of what's going on here. Now, one thing I would like to impress upon you is that throughout this whole process, okay, everywhere we go, I'm going to highlight them, we have equilibrium arrows, okay? So we're driving this equilibrium in the lab one of several ways, okay, or combinations of ways. Might be using a huge excess of that, okay? We might be distilling the water as it's formed, so on and so forth, using a special apparatus. Any number of means. But it also means that you could start here at the bottom. Okay? You could start here at the bottom and work your way back around using essentially the same set of curved arrows, only going the opposite direction. So this process could start here to get to there, or it can start here to get back to there. Okay? But we're going to do it in a forward sense. So here's your catalyst. All right, let me make a note of that. That's our catalyst. So what does that mean? It means that it's going to speed up the reaction, and it's going to come back at the very end of the reaction as well. Now you saw this earlier when we were looking at the reaction with amines, that the carbonyl oxygen, okay, gets protonated, and that's going to make this into a much more potent electrophile than it was prior to that. Well, what do electrophiles need? They need nucleophiles. Now look here. How many moles of water do we have? We have 2 moles of water for every 1 mole of ketone. Or you can use the word equivalence, or you can even use the word molecule. So I'm going to write this. Let me just write this. This is our first equivalent, okay? First equivalent, because there's 2. Now if you don't like the word equivalent, go ahead and use the word mole. If you don't like the word mole, go ahead and use the word molecule. You can use those pretty much interchangeably. Alright, so what's this going to do? What it's going to do, it's going to act as a nucleophile, okay? To this carbon. Remember, this carbon now is very electrophilic. And then these pair of electrons will become a lone pair on what's now an sp3 oxygen atom. So this is our second intermediate. Now you've kind of seen this before when we're looking at the enamine formation, that we're going to have an intramolecular proton transfer, okay, there. And it can be intermolecular or both. Point is, we're going to convert that into a good leaving group. And then what happens next? What happens next is that the water molecule is going to leave, is going to depart, it's a leaving group. And when that happens, this pair of electrons could actually collapse in between here, all right? And that would give you this. And so here's the water, okay? There's the water that came off of that intermediate. Now this intermediate here is resonance stabilized, and we're looking at either one. This would be the dominant form because we have complete octets around that carbon and the oxygen. Either way you want to do that's fine. But here's our second equivalent of methanol. Okay? And so what can it do? You can show a curved arrow going from here to here, or here to here. Either way you want to do that's fine. Let me just show it going here to this resonance form, okay? But you could go there as well, right? Let me just do it both ways. And I'll put the word or underneath it, okay? Or. But if you go this one, you need one more curved arrow, okay? All right, so what does that do? That gives you your second equivalent. Now remember, water's hanging around, and we also remember that the catalyst has to be regenerated. So once we have this nucleophilic attack at this carbon, we have this new intermediate. Water molecules here to pick up that proton, right? And then that leaves us with our final product. So here's our catalyst. Okay, our catalyst regenerated. We write catalyst regenerated. You can see it there. And here's our ketal. Okay. Or if you want to call it acetal, because that's the more general name. It's a ketal because it came from a ketone, but it belongs to a category called acetals. Now, for practice, they want to start here and just work your way backwards. Okay, we'll go all the way the other way, because then you will appreciate how this works as an equilibrium process. All right, so that's how you form a ketal. Now, we haven't said too much of why would you want to do that. Okay, nature does that actually, but here's why we might want to do it in the lab. And it's under the heading of, we call it acetals as protecting groups. Now, there's actually books out there. I actually have one. There's an entire book dealing with nothing but protecting groups. Okay, so you might wonder, what are protecting groups? Well, a protecting group is to protect a certain functional group, so that you can do other reactions on a molecule without damaging that functional group. For those of you who may have painted a wall in your house, you might use that real colorful paint, that paint that you put along. There's some of it's fluorescent blue, there's orange, green, yellow. Then you take your brush and you paint and you get it on there. Then later you pull off that fluorescent tape and it leaves a perfect line. Well, that tape kind of protected that area behind you. Same thing with protecting groups. So we're going to install an acetal protecting group, and then once we do the reaction, we're going to take it off. Okay, the same way we put it on. Now, to understand the scope of this, let me read this scenario to you. In addition to the ester carbonyl, lithium aluminum hydride will reduce the carbonyl, ketone carbonyl as well. All right. Suppose you wanted to reduce an ester group to a primary alcohol using lithium aluminum hydride, but leave the ketone carbonyl alone. Okay. Leave it alone. We don't want to damage it. So it's imperative that you protect the ketone carbonyl using an acetal. So let me show you what I'm talking about. Basically, what I have here are two sets of reactions. Okay. So let's just look at the one on top first. Okay. So this might be something that you recognized when we were back in chapter 17. What functional groups do you notice that we have here? Well, over here on the left we have what? we have a ketone. Okay? And what do we have here on the right? We have an ester. Okay? So if you were to take this molecule and you were to add lithium aluminum hydride and quench it with water, what would happen? You're going to reduce both of the carbonyls. You're going to reduce expectedly the ester carbonyl to this primary alcohol, and expectedly you're going to reduce the ketone to a secondary alcohol. Okay, you end up with this diol here. Okay, and by the way, here's your byproduct, and we'll talk about that. But what if you didn't want to reduce that? In other words, let's suppose, well, I didn't want to reduce the carbonyl. I wanted to leave that carbonyl alone so I can do something else to it later. Well, what if you could put something around it, okay, to protect it, or something on it to protect it? That's what the second reaction is, okay? So what we're going to do, we're going to use ethylene glycol. This is ethylene, which is a diol. Ethylene glycol. It's a 1,2 diol and a catalytic amount of acid to do what? Protect this carbonyl. So this scheme you're looking at here is protection. Okay? This is our protection. No longer do you have a carbonyl, right? Instead, you've bridged it with the this ethylene moiety, right? Using this diol. Remember, the previous page we had two equivalents of alcohol. Well, in effect, here we have two OHs. So we're going to form the same kind of thing. We're going to have a protected intermediate here. So what is this intermediate called? This is our ketal, because it came from a ketone, right? So we have it on there. Now, you only protect ketone carbonyls or aldehydic carbonyls. This does not react with the ester, okay? It does not. So this is going to stay as is. So I want you to contrast this structure to that structure. Now, let's carry out the same reduction that we did on the top page. And these are our reducing agent, right? What's it going to reduce? Well, the only thing that it can reduce is something with a carbonyl. And so it's going to reduce the ester just like we did up here in the previous one, okay? See, the reduction is the same, but there's no reduction took place there because there's no carbonyl. Now, how did I say you put these on? You have to use what? Catalytic quantities of acid. Well, how do you take them off? Catalytic quantities of acid. So the scheme you're looking at here is the opposite of protection. This is called deprotection, okay? So we're removing the protecting group and we're restoring the carbonyl, right? There it is. And of course, there's your byproduct that came from the protecting group. So you may have to dwell upon this a little bit, but again, contrast this structure to that structure, and notice here, this had the ketone reduced to a secondary alcohol, where here is the ketones the same. So this took added steps, but protecting groups are very integral to organic chemistry. So, and I had mentioned this again, you may have taken notice that acetals are installed. Okay, in other words, right here, they're installed using an acid catalyst, and similarly, you may have noticed that's also removed. And we call that deprotection with acid catalysts. And so in order to favor the equilibrium, okay, we apply Le Chatelier's principle in the lab using specialized glassware and or solvents or combinations thereof in order to accomplish that set objective. All right. Okay, now I'm going to move into really the most important, most cool part of this particular chapter, and it's called nucleophilic addition of phosphorus ylides. Okay, now we had the word ylide in the lab when we were talking about the conversion of benzaldehyde to benzoin. And this is called the Wittig reaction. Okay, it's a German word, obviously. This is one of the top 10, maybe even top 5 important organic reactions. So it's very important. And why is it important? Because you can convert carbonyl compounds into alkenes. Now remember, we had a whole chapter set aside for alkenes, so imagine if you produce an alkene, the things you can do with it. So George Wittig actually won the Nobel Prize in chemistry for this, right? And so what I've given you here is sort of a general depiction of what's going on. Sometimes it's called the Wittig olefination, right? Now the word olefination comes from the word olefin, which just means alkene, right? It just means you're going to make an alkene out of an aldehyde or a ketone. So as a general example, here in the middle of the page, sort of, this is a ketone. Let me just write above it. And this is an aldehyde. These are called Wittig reagents. Sometimes they're called ylids, and other times they're even called phosphorines. Okay, that's what they are. These are your Wittig reagents. And what are they there for? They're there to produce, in both cases, alkenes. So this is an alkene. This is an alkene. All right. And of course, you very poor atom economy, because you end up with all these byproduct and have a molecular weight usually more greater than the alkene itself. So one thing that we always said about the Wittig reaction, even though it's one of the best, okay, is the very poor atom economy. Okay. Poor atom economy, because this is triphenylphosphine. There's 3 benzene rings there, guys, phosphorus and oxygen. It's poor atom economy. But if you could figure out a way to recycle this, okay, back into, just taking that oxygen off, you make a fortune. It turned that into a good atom economy. So let's talk a little bit more about the Wittig reagent, then I'll show you how they work. To begin with, this is a 3 benzene rings, and it's a pH reverse bisphenol attached to a phosphorus and double bond carbon. It's called an ylid. It's pronounced ylid. Ylid. Okay. And sometimes they're called Wittig reagents, and sometimes they're called phosphorines. I tend to use these terms interchangeably, but they're very unique. What makes them unique? What makes them unique is they have opposite charges on adjacent atoms. So if anybody ever asks you, okay, might do that. What's unique about it? They have opposite charges on adjacent atoms. You say, well, that's cool, but can't I just put this pair of electrons in here and draw that resonance form? Wouldn't that work? Yeah, it would, but this is the dominant resonance form. You wouldn't have thought that back in organic chemistry 1, right? This is the dominant resonance form. Say, wow, why is it? Here's why. Let me write dominant resonance form. And I'm referring to this one. Because, folks, if I put that pair of electrons there, it's going to pull the phosphorus and the carbon closer together to give it more of a double bond character. Okay? So what's the problem with that? Well, these are 3 benzene rings, 3 phenyl rings, and they're bulky. And it's kind of hard to pull things in closer to that phosphorus, okay? Simply on that basis, because it creates too much congestion. Yeah. So we want this bond, we want to keep this bond kind of long, right? Which is good because this can now serve as a nucleophile, right? It means that pair of electrons is pretty available. So this pair of electrons here that you're looking at, pretty much available because it doesn't have the double bond character. Now, that being said, sometimes we still draw it that way. Okay, it's just understood that this carbon is a nucleophile, and it's what's going to attack carbonyl. So, ylids are synthesized by condensing triphenylphosphine in a suitable alkyl halide, and we're going to treat with a very strong base. Let me show you one of those. Here's a common one. Show you how this works. Here's triphenylphosphine. Okay. Before we just wrote it down as this, but now you can actually see the structure. So it's a nucleophile, and it's going to collide with that carbon bearing a leaving group. So where have you seen this before? It's the same as an SN2, right? SN2 reaction. And so we end up with this salt. Now, I've explicitly shown one of the three hydrogens in the methyl group here with the bond. Well, it turns out they're not very acidic. Not very acidic at all. I think the pK is like about 35 or something like that. But this is a really strong base, N-butyllithium. Let me draw N-butyllithium. I'll just draw the basic part of it. N-butyllithium is a very powerful base, as I've already said. Okay, extremely powerful because it's the conjugate base of extremely weak acid, butane. Okay. And generally these are in organic solvents. They're very pyrophoric, but they're really strong bases. Okay, it's like a Grignard reagent. So what's it going to do? Folks, it's going to come here, remove that proton, and leave the pair of electrons behind on that carbon. So you can see the dominant resonance form here. There it is. Dominant resonance form. This is now nucleophile. So this would be a way to add a CH2 to a carbonyl. So you can choose different alkyl halides here to make different phosphoranes. It just depends on what you want to make. So I'd like to take you from basically here to the alkene, and let me show you that on the next page. Okay, and I'll let you read these few bullet points at the end of page 137 on your own. What we have here on top of page 138 is a system set up for understanding how the Wittig reaction works. Okay, so it says provide a detailed step-by-step mechanism for the following general Wittig olefination reaction. So we're going to take this Wittig reagent on the left, this generic ketone, and this could have been an aldehyde, to show how we produce this alkene and how we also get the triphenylphosphine oxide as a byproduct. Now there's nothing here that you haven't seen before. You know that step 1 is going to involve this carbon acting as a nucleophile to the carbonyl. Then we're going to get that pi bond breaking, just like I've shown there, and place that lone pair onto the now sp3 oxygen. So we're going to set up an equilibrium. Okay, let me show you how that would work. Okay. To get a kind of a firm grasp of how this is going to work, let me kind of sketch this out very carefully. And make this drawing kind of big so you can see everything going on really well. Alright. I need to put things in the proper orientation so that it'll make sense. There's that phosphorus. Okay, and here are the two hydrogens that were bonded to the Wittig reagent. And over here we have the two R groups. Okay, one of these could be hydrogen, these R groups can be different. And now you know that this oxygen is negatively charged. And we have 3 phenyl rings attached to this phosphorus. Okay, so you can draw in all 3 of them, or you can abbreviate like this. Put 3 there. Now what McMurray does, he puts those in brackets. Okay, which is fine. You can do that too, but I just might as well show it like that. There's no harm, no foul. So this would be the first intermediate we get. And so where's the new bond? Where's the new bond? The new bond is right there, right? There's your new bond. Carbon-carbon bond. Anything that produces the carbon-carbon bond is good. What do you think is going to happen next? Well, you can see that the phosphorus is going to be ended up bonded to that oxygen in this intermediate, right? So we can show one of these lone pairs, okay, forming a covalent bond with that phosphorus. Now you know that phosphorus and oxygen is notorious for forming really strong bonds. Okay, we see that in our biological processes all the time as well. So we're going to make this strained four-membered ring by virtue of that particular process. So let's draw that out. Let's draw out the net result of what would happen by virtue of that oxygen forming a covalent linkage with that phosphorus on the adjacent side. So that's all we've done. Here are those two R groups. Okay, let me put in the lone pairs. And so this is an intermediate. Okay. Right, then you say, well, that's cool and that's all fine, but how do we go to our product? I'm going to draw the product with an arrow going that way, because odds of it reversing are pretty slim, right? Because the entropy wouldn't be favored to do that, but we're also going to produce a double bond, two sets of double bonds actually. So this is a highly favored forward reaction. Now, the way that you can show curved arrows from going from here to there, from this intermediate to there, there's more than one way. But why don't we just show the double bond being produced here, like that, and that double bond being produced like this, okay? So if you follow those curved arrows, you get to your alkene product. And this is why you did the reaction, to make that alkene product. And you also get this byproduct, which has a very high molecular weight, and this is called triphenylphosphine oxide. Okay, triphenylphosphine oxide. Alright, so that's it. Got two more Wittig reactions to look at here, and then we'll take a break. Okay. Let's complete the following Wittig reaction. Okay, and then it says, take note that I've guessed the phosphorine in its minor resonance form. This is the minor resonance form. Anytime you see the Wittig reagent with no charges, you know it's the minor, but that's okay. And then Murray shows the charge separated resonance form. Alright, so I'll draw both of them for you, but bear in mind they really mean the same thing. So if you show the charge separated resonance form, all that would mean is that you have, rather than a double bond there, you have a single bond there. Okay, and this would be plus charge, and this would be negatively charged. But it's kind of convenient to do that. It just saves a lot of time. Irrespective of this, you know what's going to happen, right? This carbon is going to act as a nucleophile of that carbonyl. And everything that you see up there is going to ensue. So one reason I kind of like to do it this way is I can see exactly what's going to happen. Folks, everything I highlighted in yellow is going to substitute for that. Okay? We're basically going to swap those out. On both sides, actually. So what would that look like? Here's what it would look like. Where you formerly had doubly bonded oxygen, now you have the doubly bonded carbon. There's your product. Okay? This is your organic product. This is why you did this reaction. Now if you want, okay, you could have shown it this way. Put the carbon there, with that one hydrogen out like that, and the methyl group out like that. That looks a little neater actually. Right. But either way you do it, it's fine with me. Just bear in mind the reason you did this reaction, okay, was to make this organic product. This is your major organic product. And it's called major because that's why you did it. And there's a lot of atoms left over here too. But this can be separated and find a way to recycle it perhaps. Let's go to the bottom of page 138 before we take our next break. And here we're going to try to figure out, okay, what Wittig reagent will go in this box if you wanted to make that alkene. The way to do that is just to remember what's going on with the Wittig reaction. What I'm going to begin with is I'm going to draw a squiggly line, okay, between the two sp2 carbons, because I know that this half of the molecule is going to become incorporated into that half of the molecule, okay, using the Wittig reaction. See? See, this is acetone. See all those carbons there? Those are the same carbons over here. You have to find a way to install this. So, one good way to do that is to simply sketch what you see there. Okay, let's do that. Here's that carbon, right? And there's a methylene. Okay, now we have our aromatic ring, so on and so forth. Cruising along here. There's our ring inside there. Here's that hydrogen. Okay, we're getting closer and closer. And what do we need to do? Well, we're going to put a phosphorane in here, right? But it says you can put it in its minor reference form. In other words, you can sketch it like that. Or if you want, you can draw it in the charge separated form. Either way is fine with me. So that means you have to change the gears a little bit. Okay, there's a double bond. Here's the phosphorus. And here are the 3 phenyl rings. Okay, so this is your phosphorane that you would need in order to take acetone, this, to make that really complex alkene. Okay, so I think we've reached another good place to stop in this really long chapter. And when we come back, okay, we'll finish up chapter 19. Talk to you later.